I'm Sergey Goncharov from Friedrich Alexander Universität Langen-Nuremberg. I will be talking about uniform Elgot iteration in foundations. So I will start with a very high-level message, which is not directly related to the talk. So this is just meant to be very high, very high level. In case if you forget everything else, maybe you would remember this. So I just wanted to note that in some recent decades, I have been seeing a lot of movement in this direction from mathematics to type theory, which is related to various reasons. With formalizing mathematics and proof assistance with Vygotsky's program, with successes of homotopy type theory and dependently type languages. So what I wanted to say is that I think this work would profit if one thinks a bit more about factoring this direction like this. So going from mathematics to a category theory and so on, and to type theory. So basically, like working with categorical abstractions of notions, results, and so on, and then transferring them in the type theory in this form, because I know that this is not always done this way. So I'm seeing several reasons why, type theoretic formalization would benefit from it. Because it's you maintain people, you maintain results, and you make the results more general. And I'm seeing this also as a way to be unbiased about a particular choice of foundations, of a particular choice of type theory principles, like axiom of choice, or various versions of axiom of choice, exclude middle, and so on. So being unbiased, basically, and Martin Escardo used this nice term, neutral mathematics, for this, if I understood it correctly. So I really like it, and so I suggest to regard this my contribution as a contribution to neutral mathematics. So let me put some context first. So this work is a work about the notion of partiality, and there are some existing related work on partiality monads. I would specifically mention these three papers: Chapman, Ustul, and Veltri, who introduced a partiality monad using co-induction and quotieting, and then Alternkirch and Danielson Krauss presented a different approach, by constructing it using an inductive type in type theory. Then there is this recent work by Escardo and Knapp, who compared these two things and basically argued that it's not that you can prefer one over the other; they are sort of both important, and yes, the problem is they are generally not equivalent, and so they suggested to use. Instead of using a monad as in the previous work, they suggested to use a certain category of discipline map. Then there is another direction, completely different, related work on iteration. I will relate to the work on Elgot algebras and Elgot monads. These are this work by Adam McMillus and available on formalizing a notion of iteration by monads. So what I contribute here is a specific version of partiality monad, which I call K. Meaning that K is slightly weaker than L, which is a traditional name for partiality monads. I show various results listed here about K from very first principles that define K and relate this monad both to classical mathematics and to constructive mathematics in different ways. So in order to motivate and present a very basic idea about it, I suggest to look at this kind of morphisms from S to the coproduct S plus S, which you can regard as the simplest possible computation. so which either continues as or finishes in X producing a certain value. And then there are two types of behavior. So the process like this, it can converge infinitely number of steps by producing some xn, or it can diverge because it can run forever. So well, the question that I'm asking here is, what is the generated domain of denotation kx? So which would include all the generated material by such processes. So they must include all values from X corresponding to the convergent branches, and they also must include divergence. And we can try to define Kx to be a free structure which supports an iteration operator and these two principles, which are really basic and uncontroversial. So we would like to say that, well, that iteration operator unfolds a process, and then it must satisfy the fixed point law, and then uniformity principle, which I will revisit later. It's basically saying that, so the result of the computation doesn't depend on the particular shape of the state space. So I call such structures uniform iteration algebras, and Kx is meant to be the free uniform iteration algebra. So, and this definition is related to Elgot monads. So Elgot monads, yeah, they were introduced by Dan McMillius and Vallabille, like I mentioned, and so the K supports this kind of iteration operator, while Elgot monads support slightly more, or maybe considerably more, general type of the iteration operator. So you see here this X, the recursion variable, it can occur under T, while here it's not allowed to occur under the functor. Well, in particular because K is not defined as a functor. So we define the free algebra, and then that's provable that K extends to the functor. So, and arguably, Elgot monads are the right thing to interpret while loops. And they satisfy the axioms which are similar to the axioms modulo this typing of the fixed point operator, similar to the axioms of the uniform iteration algebra. In particular, we have this fixed point law and the string diagram form, and this is what uniformity means. It means basically if you commute, I can commute f over h, so this indicates that h is a side-effecting function, and obtain h and then followed by g. So if you do this forever, then you can, if you compose this h with g, in a loop, then you can commute h over g and keep postponing it to infinity. And so because of this law and the premise, what you would obtain would be just a fixed point of f. There are two more laws, which are called naturality and codiagonal, and they're easier. They are basically just coherence law. If you have a loop like this, then you can stretch it like this, and that would be the same, would have the same semantics, but in terms of algebraic expression, that would be two different expressions. And then the codiagonal is another law, somewhat similar to Beckich, to the Beckich law. Yeah, and that's the laws which govern Elgot monads, and we had several papers with authors arguing that this is the right abstraction over, well, all while languages, more abstract, and strong Elgot monads, so it's a superclass of the monads where the iteration operator is computed by the least fixed point argument, but they contain properly more examples of monads. In particular, if you start with an Elgot monad and form this so-called resumption monad, so it's it's a monad obtained by applying the greatest fixed point operator to this expression. Then the obtained type captures something that can be roughly called generalized processes over T. T understood as the computation effect. And this monad is again an Elgot monad, but it's not, so the fixed point operator for it, the dagger, is not induced by, well, at least it's not directly a least fixed point operator. So, and yeah, this is a very nice class of monads, and one would wish to form the initial Elgot monad. But the problem is that in contrast to the uniform iteration monads, so the uniform iteration algebras, this is an imperticative definition, because because the type of the dagger, it already talks about the monad. So this monad must be a functor which has some arguments, and then we formulate some laws of these monads with respect to our assumption that's well, that it's a monad already. While for the uniform iteration monads, we don't do anything like this. We just form a free algebra, and then it's provable that we can get a functor out of it. So yes, it's one of the reasons why the uniform iteration algebras, free ones, they are more basic structure than Elgot monads and initial Elgot monads. I will start with presenting our assumptions. So I'm working very generally, so I'm just fixing an ambient category, so it's very basic, subject to very basic constraints like products, coproducts, extensivity, existence of the natural number object, and then I'm assuming, which must be stable, so parameterized natural numbers, and I'm assuming that the exponentials of this form exist. So the category needn't be Cartesian closed. So that, for example, would work in topological spaces, which are not Cartesian closed. And you see there are lots of examples satisfying these constraints. So perhaps the category of topological space is the most interesting example, because it's a category which fails lots of other assumptions, more restrictive ones. Okay, and then I recall the delay monad. So the delay monad is just a spinal coalgebra, which is induced by two operations, co-generated if you wish. So we have elements X, which corresponds to the computation which finished now, or we can postpone the result until later. So, and we can postpone infinitely, so you you get the infinite computation there. So, differently put, we can understand dx as the type of inference streams over x unified with the divergence element, which contains an element of x not more than in one place. So, and of course, you might wonder, okay, if it's like this, it's either one element occurs sometime or it never occurs. Don't we have a distinction between, well, an element plus the position in the stream and infinity? Well, that's true from the classical mathematics perspective. Well, constructivists call it limited principal omniscience. So, and categorically, it can be formulated in this way. That the natural number objects, the natural number object n, well, the embedding of it into D of 1, which can be understood as connatural numbers, so not necessarily finite numbers, that this is a coproduct injection. So this is equivalent to saying that the delay monad is precisely isomorphic to this expression x times n plus 1. And yeah, if you adopt the limited principal omniscience, then lots of things just get very easy. So then you can check that already under our assumptions, K is isomorphically a maybe monad, and it's the initial Elgot monad, and it's enriched over pointed omega complete partial orders, and it's also a free pointed omega complete partial order on X. And yeah, there are lots of classical examples and some semi-classical examples like pre-sheaf toposes. So these are need not be Boolean toposes, but they still inherit some degree of excluded middle sufficient to prove a limited principle of omniscience. And for all these examples, all this is true. And the non-examples prominently feature topological spaces again. Non-pathological realizability toposes do not support limited principle of omniscience. And of course, PW toposes of sets in the homotopy type theory and setoids. So these are examples relevant in the scope of constructive mathematics. Okay, but the question is, okay, if we do not have a limited principle of omniscience, how much properties of K would survive? And that's basically the answer, that's the main contribution. So one can prove the following. So first of all, if Kx exists, all these free algebras exist and are stable, then it's probable that K is a strong monad. So it's a monad, it's strong, it's commutative, and it satisfies this funny law, which in conjunction with commutativity means that it's an equation lifting monad. So being an equation lifting monad is a very restrictive condition. It basically says that K, equationally has the same properties of as lifting monads in categories of domains. So they just support basically the non-termination as the only effect. Then class category of K is the restriction category, yet another notion, which means that we can compare them in particular, and then we can formulate what is the domain of definiteness of every morphism. Then they further, so the operation of the monad respect all the partial order structure, including the divergence. So classic composition is left strict and right strict. And then one can additionally prove that the dagger, not the dagger operation, the iteration operator is an internal order limit of finite approximation. So this is a form of Kleene fixed point theorem. So the iteration is omega reachable by finite approximations. Okay, and then another thing is we can, there is a related notion introduced previously by Adam McMillius and Melville. Basically, the idea is that the delay monad can be axiomatized in a similar way. We can introduce an iteration operator for it, but then we need, when unfolding the iteration, we additionally need to add delays. So, and then, so it's shown, it's one of the implications of this work, that D is then completely axiomatized in terms of this operator. It's subject to 3 axioms: fixed point uniformity, analogous to the previous ones, plus a law of compositionality I didn't introduce before. So, and now you can try to think of K as a collapse of D by removing the delays. And you've seen already what means fixed point and uniformity without delays, and compositionality without delays looks like this. So it's basically looks like yet another occurrence law. So we've got this loop here locally for F, and we can stretch it around H2. So, and you see diagrammatically this is isomorphic. So you would expect this one to be true, but it's a different axiom. It's not, it's independent from the other two. And yeah, it follows that actually this axiom of compositionality follows for K. So because of freeness, this algebra, which satisfies the first 2 laws, it's completely non-trivial. So, but it follows from the from this previous characterization of K that I showed you, basically from the cleanest fixed point theory. Okay, and then another relation is to quotient in the procedure of the delay monad. You can, following this original idea by Chapman, Ustal, and Veltri, you can, again, regarding this dx as a sub-object of the object of partial streams over x, you can say, okay, we identify two streams where, well, by this relation, saying that if they are equal, if we can reach a value at some position in one stream, then we can reach the same value at some position by another stream, and vice versa. So, and yeah, it's also not so easy to formalize this in our generic settings categorically. So I suggest to do it like this. So basically we define this D wave object as this co-equalizer. So we are equalizing these two arrows here, which basically say, okay, if I have, well, a computation with x times n, so x in a number at some point, so I can either just forget the number, or I can, yeah, I can apply, so this iota, that's an embedding of x times n to d. So I can first cast this x times n to d, and then apply the multiplication of the monad. So with this definition, you can show this law that rho basically kills delays as we wanted, but the law itself seems to be weaker than this. So it's not that you can, well, it doesn't look so that you can simplify this co-equalizer by saying that just rho co-equalizes delay and identity. And then you can prove lots of, well, few things based on this definition. I mentioned three, there are a bit more in the paper. So these three things are equivalent, that the co-equalizer is preserved by D, or that D tilde extends to a strong monad, and rho is a strong monad morphism, and that D tilde is equivalent to Kx. D tilde is isomorphic to K, and rho is an iteration preserving morphism. So this could be regarded as a way to obtain K by quotienting D. But that's not for free. We need to make sure that this co-equalizer is preserved. So, and if we additionally assume something stronger, that this co-equalizer is preserved by this exponentiation by natural number, then it entails a Fourier's condition, and also modulo an additional assumption that the category C is exact. For example, a pre-topos, then D tilde is additionally an Elgot one. This satisfies a couple of other conditions. But yeah, so the takeaway here is that this is a kind of a way to enforce the law, the axiom of countable choice in a generic way, in generic categorical formulation. So there are quite a few things that I would like to do next. So I would like to do it in Agda and formalize it in Agda. And of course, the question is, this is related to my very first slide. Okay, but how to formalize a category? There are several proposals to this effect. Yeah, so one can choose one or contribute into improving this. Yeah, so then there are a couple of questions like not covered yet, like so a concrete separating example for K not being an initial Elgot monad, and relate, yeah, so the initial Elgot monad and another construction exists in the literature, which I also mentioned by constructing the free-pointed omega CPO. Yeah, also considering different other sort of formats for recursion by considering more complex functors and yeah, using different set of semantics. Okay, this is it. Thank you.